Hey guys, this is Gary, and this is lesson 3 on how computers work. So we've been talking a lot the last few days about how computers store all of the information that we use on a computer. So what we started off talking about was there's this idea of a bit. And a bit is the combination of the words binary and digit. So what binary means is two choices for each digit. And so 1 bit is the smallest unit of memory on your computer. And on a computer, well, I really misspelled that word, computer. And what you can think about with memory, I think it's a useful idea. We often think about in our brains like storing something in a space. Your computer is physically doing that. It stores a piece of information in an open slot, and that information is always going to be represented using a binary digit, a 1 or a 0. Now, that's not too interesting, and you can't store very many things if you're just thinking either a 1 or a 0. So what we saw last time was that it was useful, instead of taking 1 bit, to take 8 bits and combine them. And we started to call that a byte. So 1 byte is just 8 bits. And inside of your computer memory, that would look something like this. It would be 8 slots. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I did a not so great job at making those symmetrical, but it's okay. And each one of these is a bit. So it'd be something like 0, 1, 1, 1, 0, 1, 0, 1. And this whole thing is called a byte. Now, the reason why we expanded to 8 bits in particular was the thing that we were trying to do last time was we were trying to represent letters in the English alphabet. And so for letters in the English alphabet, we saw that we needed at least 64 options. But then we wanted to add in different letters, like letters with accents and letters with NYAs and things like that. And we saw that we had to expand the number of possible options quite a bit. And that actually required us to have 8 bits worth of data. So we're going to talk more about those choices in a second. But this was just like a kind of an accidental choice, 8 bits. And then it became very popular because it was the right number of bits for English letters. All of us have heard of the word byte before, so this continues to be a major part of computer science today. So what range of numbers can be represented using a byte of data? So if you think about a byte of data could be is 8 spots. And instead of drawing it like I did before, I'm just going to draw those 8 spots like this. And when you think about the range of possible numbers that can be represented using this data, well, you could say, okay, well, for all of these, you have 2 choices, right? This is going to be 0 or 1, 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 0 or 1. So that would be one combination. What we're wondering here is how many combinations we can make total. So we have 2 choices for this one. 0 or 1 here, 2 choices 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 here. And just like in the last problem set, we saw that we had to multiply these together to get the total number of possible combinations. So if you do that, 2 to the 8th on your calculator, you find that you get the number 256. So in a full sentence, there are 256 combinations possible with a byte of data. So if we think about numbers, it's reasonable to think, okay, well, we could start with the number 0. And with 256 combinations, 0 uses one of them, so we have 255 leftover combinations, so we can represent the numbers from 0 to 255. And I wrote 225. That should be 255. It is possible to represent the numbers from 0 to 255 with 1 byte of data. And as an added check on this, let's just prove it really quick. If you think 0, 0, 0, 0, Well, for a byte, we need 8 of these, right? So 0, 0, 0, 0. That's definitely the number 0. And if we use our binary conversion, the highest possible number we could make would be if we had the highest digit for all of these. Now, usually in decimal, that'd be like 99999, but that's not what we're working with. We're working with binary. So the highest value we can put for each digit is 1, 1, 1, 1, 1, 1, 1. And if we use our place values here, this would be our 1's place, 2's place, 4's place, 8's place, 16's place, 32nds, 64ths, and 128th's place. So the highest number we can represent is one that has 128, it has 164 as well, it has 132, 116, 18, 14, 12, and 11. So let's see what this all adds up to. This plus this is 130. This plus this is 80. This plus this is 40. This plus this is 5. This plus this is 120, 130, 120, and 5. 255. And so we see proof mathematically that the lowest binary number we can make is 0, and the highest binary number we can make is 255, just like we saw over here in the green writing. All right. But binary numbers were not the main purpose for introducing bytes, right? The thing that drove us to talk about bytes was this idea of trying to convert binary to English. So let's take a moment and review that. So we've got a secret message here in binary, and we want to convert it to English. So this is what your computer does when you click on a file. It sees a whole bunch of zeros and ones, and it knows to convert that to a letter. So let's take a look at this first one here. 0, 1, 0, 0, 1, 0, 0. So in order to convert that to binary, our table's not very, or to English, our table's not very helpful, our ASCII table. We need to convert it to the decimal code first. So we do the same thing we did before. 1, 2, not 3. 1, 2, 4, 8, 16, 32, 64, 128. So we have a 64 and an 8. That would give us 72. And if we convert a 72 to ASCII, that is an H. All right, cool. So I'm going to encourage you guys to test the rest of these. You should find that the word is a familiar 5-letter word, but you'll have to go from binary, like this one, to decimal, just using the binary number conversion method like we did here. And then finally, you'll be able to use ASCII to convert it to a letter. And this is what your computer is doing with all of the data that's stored on it. Now at this moment, I think it's interesting to pause for a second before we continue with today's lesson. If you look at the back of your smartphone or you look inside of the settings on your computer, you can actually look and you can see how much data your computer stores. So looking at the back of my phone, oh, it's not on the back anymore. It used to be on the back. You can go into the settings on your phone. You can't see me doing that, but I'm gonna do that right now. Go into the settings and look at my iPhone storage, which is almost full. And not now. Let's see, storage. It says I have 32 gigabytes of space on my iPhone. So giga actually means billions of bytes. So I have 32 billion bytes. And that's really wild. You have 32 billion, so that's this number right here, bytes. And bytes are these 8-bit combinations inside of your phone. So if you want to know the total number of bits that you have in your phone, you could do this number times 8, because each of these is 8 bytes, or each byte is 8 bits. Bits. Okay. So 32 times 8 is 256 billion bytes, or billion bits. So we have this many zeros or ones inside of our phone hard drive. And all of those zeros and ones inside of our phone drive make up all of the apps that we use, all of the text messages that are in its memory, all of the pictures that you take, all of the videos. And a key component, right, of the information that's being shown on your phone or stored on your phone is the ability to represent colors. And I think colors are a pretty interesting way of continuing how we look at how computers represent data. So we saw briefly that representing a black and white image is actually pretty straightforward. You could just say, okay, this is a 0, so it's not lit. This is a 1, 1, and then 0. So the ones are pixels that are completely on, and the zeros would be pixels that are off. For color images, things get a little bit more complicated. So if you zoom in inside of your phone screen, you can see that your phone screen is subdivided into little boxes. This is the same thing that happens when you take an image and you zoom in too close on the image. It starts to get really boxy. And so you notice that maybe this pixel is red, and then this pixel is green, and the whole pixels are each a single color. This is actually part of the hardware of how your phone is built. So it turns out that your phone screen actually is just built up of a whole bunch of boxes like this, and that box gets lit up a certain color. Those boxes are called pixels. So pixels are the smallest boxes of color that can be lit up on your phone, that can be lit up on your screen. We build images and movies out of pixels. So really, when your computer stores an image, what it's doing is it's storing a list of what color each of these pixels should be. And when your computer stores a movie, it's recording a list of, for each frame of that movie, you guys have worked with frames before in your editing classes, for each frame of that movie, what will that picture look like? What color should this be? What color should this be? So before we get some more detailed information on those pixels, let's calculate how many pixels our computer screens actually have. So old computer screens only had a resolution of 480 pixels by 640 pixels. So what that would mean would be, it would be 480 little squares this way by 640 little squares this way. So let's see how many that would be. We can just do that calculation on here actually. 480 times 640, 307,200 pixels. So for an image that took up the whole screen, or an app that you're running that was taking up the whole screen, your computer would have to make a decision, which is what color are each of these 307,200 pixels? If you guys have ever worked with digital photography, it takes a lot of memory, because when you take a high resolution photo, it stores information about the colors of all of the pixels in that photo. But that makes it really nice for editing, right? Because you have all of the data still there. All right, so the modern computer screens, on the other hand, are usually something like 1080 pixels by 1920 pixels. So let's see how many pixels this would be. So the calculation that you do to calculate the total number of pixels is length times width. And that would tell you that it was 1080 by 1920. 2,073,600 pixels. Let's see if we got that right. Okay, cool. So modern computer screens are capable of displaying things at a much higher resolution with much more pixels than old computer screens. And part of that is the screen, but part of that is also the memory and the speed of the processors, right? If we're thinking about a movie and you only have to change 300,000 pixels, that's not as hard to do as changing 2 million pixels every time the frame of the movie changes. And so this happens a lot when you're watching a YouTube video. Sometimes a YouTube video will have the resolution drop down if your computer's Wi-Fi is running slowly. And that's because it can't change this many pixels, or it can't change this many pixels. So instead it settles for changing this many pixels, and it creates a grainier image. All right, so now we start to get at a more interesting question. So let's zoom in, or more interesting to me question. Let's zoom in on a single pixel. We might be curious what's actually going on inside of that pixel. So there's going to be an attached video to this lesson that I didn't make, but it's very useful, and it will show you this. If you zoom in on this pixel, what you'll notice is that inside of that pixel, it looks like a single light to our eyes. But if you're able to zoom in really closely, what you'll see inside of that pixel is it actually has 3 different lights. It has a red light, it has a green light, and it has a blue light. And these lights are so close together that when we zoom out, we can't distinguish between the 3 of them. The red, green, and blue lights all blur together. And a really interesting thing happens with those red, green, and blue lights. If you take the red light, the green light, and the blue light, by adjusting the brightness of those lights, your computer can actually make that pixel any color. So even though a pixel on your computer may look yellow, somehow it combines red, green, and blue light from those 3 different pixels to create a yellow-colored pixel. And we're going to look at this in more detail. But it's fascinating. Your computer actually has no yellow lights inside of it. It only has red, green, and blue lights. A good analogy to think about when you're thinking about combining red, green, and blue lights is to think about it's similar to the primary colors when you paint. So if you were in middle school or elementary school, you may have been given red, yellow, and blue, and you noticed that you could make any colors with those red, yellow, and blue paints. So red and yellow made orange, and then you didn't need it to start with an orange paint because you could always make it. These are the primary colors in your computer. So let me write a sentence here. Your computer uses various amounts of red, green, and blue light to make each color. So if I were hearing that from my teacher, I probably wouldn't believe my teacher because the vast majority of things that I look at don't appear to be red, green, and blue on my computer screen. So let's see. Let me prove it to you guys. So I made this web app, and basically what it lets you do is it lets you mess around with the pixels. But instead of changing one pixel, it just changes the whole screen. So right now, the red, green, and blue lights are all off. If we turn the red light completely on, our computer screen becomes red. Let's see, okay. If we turn it a little dimmer, oh no, that's annoying. It doesn't quite work on the iPad. It works very well on my computer, but it doesn't work on the iPad as well because it doesn't show the numbers. But if we turn the red light completely on, it's a very bright red. If we turn it down a little bit, it's a slightly dimmer red. Similarly, if we turn the green light completely on, it's a very bright green. Turn the green light down, but keeping the other 2 completely off, it's a dark green. To make a dark blue, we slide this one a little bit, and that makes a dark blue. But if we slide it all the way, it makes a very bright blue because only the blue light is on. So now you might be curious, well, how do we combine these? Well, if you do red and blue at full brightness, that makes sense. It creates a bright purple. If we wanted to create a darker purple, we'd have to create a darker mix of these with maybe a little bit more blue than we had red. I don't know why the counter is working now for blue. It's supposed to be working for all of these. That's annoying. All right, so to make yellow, let's see, maybe it's red and green. So red and green, for some reason, when we light up the red light and the green light completely, our eyes see that as yellow. So this computer screen is not actually yellow right now. It is a whole bunch of tiny red and green lights that you cannot see and I cannot see that our eyes can't distinguish, but when lit up, completely blend together to make yellow. All right, so you couldn't see it on that time, but something interesting happens. When we were making our websites, we started to use this color picker on Google called Color Picker, right? And we were able to set the color using the RGB values. And now I think we have the context to understand what this code actually meant. So RGB, R is the amount of red light, G is the amount of green light, and blue is the amount of blue light. So all of these values, very interestingly, range from 0 at they're completely off, and if we wanted to turn the red light completely on, it would have a value of 255. 0 to 255 would be the green light. And this one would also have a value from 0 to 255 for the blue light. So we're going to come back to that and talk about that in a second. But let's go ahead a little bit and get some practice with these. So if we look at an RGB value like this, and you can Google these if you're wanting to test your answers, but RGB 25500. The way these work is the first one is red, the second is green, the last is blue. So for this one, we've got the red light completely on and the green and blue light completely off. We looked at that before, but here it is again. So the red light completely on, and sorry, you can't look at the values. 0, 0, 116 are not right. I'm not sure why it doesn't work on the iPad. I think it's probably related to the touchscreen. But if we turn the red light completely on, it will be at 255. It looks like it makes a bright red. In this case, the green light is completely on, so it's bright green. And finally here, the blue light is completely on, so it's bright blue. Now here we've got red, green, and blue lights all completely turned off. 0, 0, 0, 0. So if we turn all of them completely off, it makes black for our screen, which makes sense. Now if we turn all of the lights to 255, then they'll all be completely on. And it makes the screen a bright white. Here, if we mix a little bit of red and some blue, this will be a dark purple. Here we mix a lot of red and a lot of blue. This is a bright pink or purple, bright magenta, I would say. Here we do 40, 40, 40. Let's see what that is. So I can't calibrate these exactly because it's messing up, but if we do like 40, 40, 40, we get a dark gray color. And so an interesting thing that you may notice as you continue to work with these RGB values is if they're all the same color, same value, 0, 0, 0, 255, 255, 40, 40, 40, they're all different shades of black, white, and gray. So then 195, 195, 195, because they're all the same, you know this is going to represent a gray value, but it's going to be a brighter gray, closer to white, because the values are closer to fully lit. So this will be a light gray color. You can Google all of these RGB values to see their exact color. You would just type that in if you wanted to check your answers. All right, so an interesting question that comes up is if I were designing this, I don't think I would have done from 0 to 255. That's a strange range of numbers. I probably would have done from like 0 to 100% turned on. But 0 to 255 wasn't an arbitrary choice. If you think about 0 to 255, we actually talked about that way early on in the lesson. That was from the Do Now. What range of numbers can be represented using 1 byte of data? And we said it was possible to represent the numbers from 0 to 255 with 1 byte of data. And so the reason why colors are constructed in this way is colors are actually constructed using 1 byte of data for each color. So RGB color values range from 0 to 255 because each light, the red, green, and blue lights, is represented by a byte of data in the computer memory. All right, so apparently the following data represents one pixel. Determine the RGB values of the pixel in decimal notation, and in words, describe what color you expect the image to be. So we just said that each of the values, R, G, and B, can range from 0 to 255. And the reason why is each value is represented by one byte of data. One byte of data is 8 bits. So to figure out the red value here, we have to select the first 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So this will be the red value. 1, 2, 3, 4, 5, 6, 7, 8. This will be, I think I got too many. Yep, I got too many. 4, 5, 6, 7, 8. This will be the green value. And this will be the blue value. So maybe you have a JPEG image, and when you look at the actual data on your computer, it's all ones and zeros. But then you double click it, and your computer loads those zeros and ones up into its memory. And it starts to read through it in order. And it knows that together this makes one color. So then it's like, okay, the first byte is going to be the red byte. So let's start by translating that one. 1, 1, 0, 1, 0, 0, 1, 1. This will be the red byte. If we translate the red byte, 1, 2, 4, 8, 16, 32, 64, 128. This will be 128 plus 64 plus 16 plus 2 plus 1. This is 80. This is 130. So 221, I believe. No, I think I got that wrong. So 130 plus 80 plus 1, that's 211. So we have 211 for the red value. Let me just write that in red because I want to... All right, next up, let's calculate the green value. So for the green value, your computer will know that the next byte, the next 8 values, is the amount of green. So 0, 1, 0, 0, 1, 1, 0, 1. Now, converting this to a decimal number, we have 1, 2, 4, 8, 16, 32, 64, 128. So we've got a 64, we've got an 8, and we've got a 4, and we've got a 1. So it looks like this is going to be 68 plus 8 is 76, plus 1 is 77. And for the blue value, let's see how lit up the blue pixel is. That was 0, 0, 0, 1, 1, 0, 0, 0 from here. And this will be 1, 2, 4, 8, 16, 32, 64, 128. So 16 plus 8, that is 24. So our total color will have 211 for the red, 77 for the green, and 24 for the blue. So I won't be able to do this exactly, but we can approximate it with the sliders because the app doesn't work as well on the iPad. So we're going to do 211 for the red, 77 for the green, and then I think it was 24 for the blue. So it's this very orangey color, and that makes sense because it was mostly red. So dark orange. Well, I'll write it with the right color here. So this should be somewhat illustrative of the scale of the amount of information that's actually stored on your computer. So if every pixel on your screen takes 24 digits, 888, 24 binary digits, 24 bits to represent. And each image you take is a huge number of pixels, something like, I don't know, 300,000 pixels. It takes a lot of your computer memory to store each image that you take. So the final thing you might be wondering is, it seems like there's an infinite number of colors that could exist. And that might be possible in real life, but it's not possible in a computer. In a computer, your computer only has a set number of colors that it can make. For the amount of red light, it ranges from 0 to 255. So you have 256 choices for the amount of red light. For the amount of green light, that's 0 to 255 as well. So you have 256 choices for the amount of green light. For the amount of blue light, that also ranges from 0 to 255. So you have 256 choices for the amount of blue light. So combining those, the same way we did before, you can multiply, just like we did with the hats and shirts and pants problem where we wanted the total number of outfits. If you have 256 times 256 times 256 choices, that means that your computer is capable of making 256 times 256 times 256 equals, 16,776,216 different colors. So your computer has this many choices for the color of each pixel. And that is pretty remarkable. So I think it's helpful to understand all of this when you're thinking about just what goes on inside of your computer. Your computer is all zeros and ones. And what we've seen so far in this unit is all of those zeros and ones can be used to make a number using a binary number conversion. They can be used to make an English letter or a letter from another alphabet using ASCII. Or they can be used to set the color of a pixel on your computer screen by using the RGB values. And we saw here, pretending to be a computer, what it would take to actually load and interpret those zeros and ones to become colors. So computers are pretty remarkable. As you think about this, I want you to start thinking about the piece of technology that you're most interested in researching for your Explore task. And thinking about things like, well, how does your computer represent sounds? That's got to be zeros and ones too. So if your technology device relies on sound, you could think about, well, how would you represent a sound using zeros and ones? Is it something that has a display screen? How many pixels does it have? Is it something that has memory? How many bytes of memory does it have? And now hopefully you understand a little bit better what all of this terminology means. So we'll keep working on this next week. I'm going to include a couple extra videos for you guys to watch today. There's no other additional problems. So have a good